Okay, hello everyone. So it's 5 p.m. now. So let's start the next online workshop in the Extended KNIME Spring Summit. But before the actual start, a couple of housekeeping information. And first and foremost, let me also introduce myself. So my name is Dora Barna. I'm an application scientist at Chemaxon, which is a cheminformatics software company and also a partner company of KNIME. I'm going to be one of the presenters today, and also here with us with the call is are my colleagues Nora Lapushnik, who is a partner relationships manager at Chemaxon, and Norbert Schasch, who is the head of the Chemaxon's consultancy team. So the three of us together will also answer your questions in the Q&A session. Now to the practical parts. So during the presentations and during the entire workshop, you can post your questions in the Q&A window, and you can also upvote the questions that you see popping up there. This is how it looks like. You can find the Q&A button at the bottom part of the Zoom window. So please post your questions there and vote up anything that sounds interesting or relevant, or if you see any issues that you also are facing. And we are going to answer some of the questions in a written form in the same window. And there will be some questions that will be answered live. And one more thing before we start with the workshop material is that this session is recorded and will be posted on YouTube, and both the link for the YouTube video and the presentation slides will be sent to you in email in the next few days. So with this, I hope that everyone have arrived. So let's start. And I will go to my next slide. So here you can see the title and the topic of today's presentation. Our title is Building a Drug Discovery Workflow in 8+1 Steps with KNIME. And what gave us the idea for this topic and for this title is that we know how popular KNIME is among the people whose work is related to chemistry or to the life sciences in general. So we wanted to share with you some examples of how various cheminformatics tools are used in a typical early phase drug discovery projects, or in those projects that are related to chemical research and discovery in general, and also, of course, of how such tasks can be accomplished in KNIME. Before we start and see what we built for you for today, some notes and information about setting up the workflow on your own computer. So first and foremost, please install the latest version of the KNIME Analytics platform if you don't have it yet on your computer. And after that, please download the workflow group file. The download information has been sent out in an email yesterday afternoon, and also today a reminder email was sent with the download link. So the workflow group file is this one that you can see here. It's called Chemaxon_KNIME_Spring Summit 2020.knar. And once you have downloaded it, please double click on it to start the file in the KNIME Analytics platform. And once it starts and once the file opens there, you will see a window that is similar to the one that you can see here on the right-hand side on my computer. So this workflow group file contains, beside the actual KNIME workflow that we will use today and which is called drug discovery workflow, so this one here, besides this workflow file, there are also every input and every configuration file, and also the final output, the final result file grouped into this KNIR file, and finally the necessary evaluation licenses can be found there along with the slides that I'm using right now. So you should have there anything that you would need to start using the workflow. And once you opened it in KNIME, you will also have to specify where you would like to ungroup the folder for this workflow group. So the default place would be the local KNIME workspace on your computer. And once you do it, you would be able to access the evaluation license files and also the PDF slides in them. And once you have imported everything, you will have to open the drug discovery workflow item in it. But before you can start using the workflow itself, then you will have to also install the Chemaxon Infocom notes. So let's see how these notes can be installed. You will have to use the URL that you can see here, and the same URL is can be found also in the PDF file with the slides in the downloaded and ungrouped workflow folder. So please copy paste it from there. This should be the easiest solution. And then go in the KNIME Analytics platform to the Help Install Software menu. And there, please click the Add button near the top of the window, the install window. And then use this copy-pasted URL and add it to the location field of this Add repository window. You will also have to give a name to the new extensions that you are going to install. And alternatively, you can also download the zipped version of these Chemaxon Infocom node extensions by using the very same URL from your web browser to download the zip file. But in either case, once you have specified the location of the extensions and hit OK, and the install wizard starts, please make sure that you select both the JChem extensions and the Marvin extensions, because we are going to use nodes from both extension or node sets. And then just follow the steps of the install wizard. And once it has finished, please do not forget to restart the KNIME Analytics platform so the nodes will be ready for usage once the software starts again. And now there are only one step which we have to take care of before we can start using the workflow and the Chemaxon nodes in them. And this step is about installing the Chemaxon and the JChem extension licenses. So as I said, both evaluation licenses can be found in the downloaded and ungrouped workflow group folder. We will first install the JChem extension license. This is the one with the .dat extension. And to install that, please go to the File Preferences menu of KNIME. And there select on the left-hand side the KNIME section. And within it, please select the JChem part. And in the opening JChem window, you will have to specify the location of this JChem extension license file. So with the browse, by using the browse window, please go in your file browser, in the file explorer, to the location of this JChem extension license file. By default, it should be in your local KNIME workspace within a folder that has the same name as the downloaded workflow group file. So locate there this .dat file, and once you have it, just hit apply and close to install the license file. And the very last step is the installation of the Chemaxon licenses, which can be done by going to your user home directory on your computer, and within it, please create a folder called Chemaxon or .chemaxon in the case you are using the Unix-based system. And within this Chemaxon folder, create another one called licenses, and then simply copy paste the license.cxl file, the Chemaxon license file, into this new folder. In the case that you are already using some Chemaxon applications on your computer, then you most probably also have these folders on your computer. So in that case, simply copy the license.cxl file to the existing folder. And after all this technical information, we are now ready to start with the material that was prepared for today. So how we will proceed is that I will continue with some introduction about what Chemaxon does and how our tools can be used from KNIME. And I would also give you a summary of the workflow that was built for today. And after this, I would also like to give you a bit more background material about the major steps of the workflow that's on the menu for today. And after this presentation, we would go to the KNIME Analytics platform, and we will also go hands-on with today's workflow. We would like to give you some 15-20 minutes to try out the workflow steps for yourself. And after this time, or after just 10 minutes of this time, we will also start answering some of the questions that you have posted in the Q&A window. And in the final part of this webinar, we will also go through together in KNIME of the major workflow steps. So this is our agenda for the webinar, for the rest of the webinar. So let's continue with the presentation part. So as an introduction, a few words, let me tell you a few words about Chemaxon and who we are and what we do. As I mentioned already, Chemaxon is a cheminformatics software company providing software solutions and various services to enhance drug discovery, as well as other chemistry-related fields with chemical and biological intelligence. And we are several toolkits and applications that can be used by those who have to work with chemistry-related data in various scenarios. So the first, a larger part of our tools can be used in those cases when someone has to extract any kind of chemical data from different sources. And these different sources can be, for example, a database or some legacy documents, scientific papers, articles, or patent documents, just to name a few. And the same set of toolkits can also be used besides this data extraction, or can also be used to convert between different chemical file formats. The second large group that we have, I would like to mention, are the most useful for those chemists who are working on designing new chemical structures or are working on optimizing the structure of molecules for various reasons. So these application set includes our Marvin chemistry editors, physical chemical property predictors, virtual library enumeration, or chemical clustering tools, among others. And finally, the third large groups includes cheminformatics toolkits and chemistry search engines that are needed in those cases when someone wants to store chemical structural information into a database, for example, to register or manage some molecules or chemical entity-related information. And these tools are also used and needed by those who want to search in databases for chemical information. And for this search, they want to use some chemical structural feature of a molecule or a reaction. So how can we access and use these Chemaxon tools from KNIME? There are two alternatives, major alternatives for that. One of those is by using the dedicated Chemaxon Infocom nodes that you have just installed. These nodes or these extensions are developed by our Japanese partner company called Infocom. And these nodes can be used on the one hand to draw chemical entities like molecules or reactions in KNIME, and also to visualize chemical structural data in KNIME. And besides those, there are several other, let's say, cheminformatics toolkits which can be used for structure-based searching, library building, property prediction, and so on and so on. And besides that, the other alternative for accessing Chemaxon applications and wiring in Chemaxon applications into a KNIME workflow is by using the REST Web Services nodes of KNIME to access various server-based Chemaxon software tools. And with this REST Web Services-based solution, we can also build in chemical structure search steps, property calculation steps, or we can also use it for managing and manipulating macromolecule related information. What you can see here is one of the two large sets or groups within the Chemaxon Infocom node collection. This group that is called the Marvin group contains the Marvin Sketch Chemistry Editor, which can be used to draw chemical structures, or the mole converter that node that we are also going to use to convert between different chemical file formats like SMICE or MRV or SDF, or the Marvin View node, which can be used to visualize chemical data in our KNIME workflow. And here you can see what we can find in the JChem extensions, among the JChem extensions. So this is a longer list where we can find nodes for property calculation, for chemical structure standardization, similarity or substructure or full structure searches, or virtual library generation or chemical clustering. Just since we are talking about an early phase drug discovery project, in those projects, very fundamental questions that the chemists have to answer is which compounds we should synthesize next. Because the final goal is to find novel molecules which can be used to have a positive effect on the biological targets in which the project team is interested in. So in the quest for these novel molecules, it's very typical that the chemists look up some already existing data, some already existing information about known active compounds that are known to show and known to have this desirable effect, desirable activity on the biological target in question. So our approach for today will be the same. Today, because first and foremost, we are going to import information and data about a set of known CNS active molecules. So these are compounds that have been tested at one point in the past and show some kind of activity on a biological target system, on a receptor that is located in the central nervous system. And after we have finished with this input data upload, just like in any other data analysis project, we will have to pre-process our imported data, clean it up, standardize, normalize everything. So once we have done it, we will be able to continue with a chemical clustering step on our imported CNS active compounds with the goal of selecting a scaffold molecule, so a compound that we will be able to use as a core structure in the next step, where we will build a virtual compound library. And once we have this chemical library of new virtual molecules, we will characterize the compounds in the library in order to select those virtual compounds which show a good physicochemical property profile from which we can expect to be able to cross the blood-brain barrier and get to the central nervous system, where they would be able to get to the receptor that we are interested in. And after that, once we have promising virtual molecules, another question that we will have to solve is to find, instead of just virtual molecules, find real, easily accessible compounds that are structurally similar to these best virtual molecules, but can be easily synthesized in the lab or have already been synthesized previously. So after this switch from virtual to real and accessible compounds, we will perform a similar physicochemical property-based filtering on the accessible compound set. And for this as well, we are going to use the so-called CNS-MPO score function to select those real analog compounds that have the best physicochemical properties that fall within the desirable property space. And after this property-based filtering, we will also use some predictive model building in order to predict the biological activity of the remaining real accessible analog compounds. And for this, we will build a binary classification model for which we are going to use our input data that also contains, besides the chemical structure of the CNS active compounds, also contains their measured biological activity values as well. And once we have made all of this information available, so we have now compounds that can be accessed and synthesized easily and also have promising physicochemical properties and can also be predicted to show some kind of activity on our target receptor. We will be able to use all this information to do the final compound triaging and select the most promising molecules from our collection, which we were able to send, for example, to our synthetic chemist colleagues and ask them to prepare these molecules for us, so that later on we will be able to continue with real tests, real assays and experiments to measure the properties of these molecules. And after this, so these are the 8 major steps of our drug discovery workflow. And the +1 step is an overlap analysis to see and check how large is the overlap of our virtual enumerated property space and the space of the real molecules that we have found in the enamine in the enamine database that we are using to find these accessible analog compounds. So by comparing the virtual and the real molecule space, we will get information about how far away we got from the original chemical space, and how large is the chance that with our accessible or real analog molecules we are exploring a new part of the chemical space. So how big is the probability that at the end of the workflow we will find some novel compounds that no one has tested previously. And here you can see the workflow, how it looks like in the KNIME Analytics platform. So most of the major steps are represented by meta nodes here, and includes several steps, some cheminformatics steps and some generic data manipulation or data filtering or joining steps. We will also have some time to try out and go hands-on with this workflow and see how it looks like. But before we do that, let's see what's behind this workflow, and let me give you a bit more background material to see how the cheminformatics looks like behind these steps and these meta nodes. So as I mentioned, first and foremost, we are going to import some input data containing known active compounds. From this, we are going to use the mole importer node from the JChem extension collection, and this input data set contains more than 3,000 compounds from the Campbell database that were tested against the human dopamine D2 receptor. This is the receptor for which we are trying to find some novel active compounds, and our input data set contains, besides the chemical structure, also the p-Campbell value of these CNS active compounds, which describes their measured biological activity values. After finishing the import, we will do some data pre-processing and cleaning. And here the key step is the standardization of the imported chemical structures in order to have a consistent chemical representation for every molecule that we are using in our workflow. We are also going to calculate the molecular weight and the formula of the standardized chemical structures with the elemental analysis node, and we will also generate the SMICE strings for these standardized molecules. And we will also use the generated SMICE values to do a duplicate row filtering, because as a result of the structure standardization, we may have ended up with duplicated SMICE values, duplicated molecules. So with this duplicate row filtering, we can remove those molecules, those standardized molecules that appear more than once in our data set. A few more words about the structure standardization. How was it done, or how it will be done in this workflow? Here you can see the standardization steps that we are using. We are going to remove any salts or smaller fragments and then explicit hydrogens that may be present in the input data. And then we are also transforming the structure of some of those functional groups which are known to have more than one chemical representation. So we will have a really consistent input data set. And then we are calculating the major tautomeric form of the imported molecules, and we are also going to aromatize them. And with this data cleaning and data standardization, our input molecules are ready for the chemical clustering step, where our goal is to select a scaffold molecule, which we will be able to use for the upcoming virtual library generation. And in this clustering step, our key node is this one, the library MCS, which can be used to perform hierarchical clustering based on finding the maximum common substructure of the molecules. So the library MCS node and clustering works in a way that it searches for the maximum common substructure, or MCS for short, of the input molecules. Here you can see how this MCS looks like for a pair of molecules that can also be found in the input data set. So in the first step, this node and the library MCS identifies the maximum common substructures of the input molecules, and then it goes to the next level and repeats this MCS search on the maximum common substructures that were identified in at the previous level, and so on and so on. So from level by level, it searches for the MCS molecules on the previous hierarchical level. So at the end, we will get let's say a simplified representation of the input molecules. This is what you can see here, for example. So in our input data set, this was one of the top level maximum common substructures that the library MCS node found for us. And when configuring the clustering, we can specify what should be the minimal size of the identified maximum common substructures. So we will not end up with a single carbon atom, let's say, as a maximum common structure of the molecules. And we can also specify what kind of features of the molecules should be matched during the MCS search. And as a result of this clustering and the following extraction of the top-level cluster molecules, we will be able to identify a scaffold molecule that appears frequently in the input data set. And then we can use this scaffold molecule to see how it's substituted and functionalized in the input molecule collection. So for this, we are using R group decomposition, where we will search for all the input molecules that contains our selected scaffold, and we will identify the different ligand positions on the scaffold that are typically filled by a substituent that is larger or different than a simple hydrogen atom. And we will, and as a result of this analysis, we will be able to select which positions we want to, or we can get some information about which positions we should functionalize in the upcoming library enumeration set. So in our case, with our input data set, there were two chemically different sites and positions on this scaffold molecule that are frequently filled with different functional groups. One of these positions was the amine nitrogen in the piperazine ring of the scaffold, while the other one was the two chemically equivalent aromatic carbon atoms in the ortho position of the benzene ring. So with this information in mind, with the selected scaffold and the most popular ligand position or substituent positions on the scaffold, we can continue with the library enumeration, virtual library enumeration, for which we are going to use 3 reaction-based virtual enumeration steps. First, we are going to functionalize the 2 ortho aromatic carbon atoms with different substitution reactions. And then we are going to use an amine alkylation virtual reactions to attach and bind substituents to the piperazine nitrogen here. let's say first the substitution, the aromatic ring substitution. For this, we are going to use two different substitution reaction scheme. First, a nucleophilic aromatic substitution reaction, and then a Friedel-Crafts type alkylation of the aromatic carbon atoms. And as a final step, we are also going to concatenate the product molecules, the resulting molecules that we get from these virtual reactions to have a more diverse virtual compound set. And then we are going to use this concatenated product molecule collection to functionalize as reactants in functionalizing the amine nitrogen. But before we go there, I would like to show you what is how these substitution reaction and virtual reaction steps can be used in KNIME. Here in this virtual reaction and virtual library building, the key step and the key node will be the bimolecular reactor node, also from the JChem extensions. For using this reactor node, we will have to specify a virtual reaction schema or virtual chemical transformation. In the first step, this will be a description schema for a nucleophilic aromatic substitution type transformation. And so we are going to use it as a generic description of transformation. And here you can see a specific reaction example for this type of transformation. And to make these transformation and virtual reactions more chemically relevant and chemically real, we can also use some reactor and reaction rules. For example, we can use a selectivity rule that you can also see here. The selectivity rule can help us deciding which aromatic carbon atom should be substituted in the reaction, and these decisions are made in our case by calculating the nucleophilicity of the aromatic carbon atoms and selecting that carbon atom that's most suitable and most susceptible for such a nucleophilic substitution reaction. The other type of reaction is a Friedel-Crafts alkylation for substituting these aromatic carbons. For this, again, we are using the same reactor node, but with a different chemical transformation that describes this alkylation reaction. And also we are using a different reaction rule set. For example, here we have a reactivity rule as well, because for this reaction to take place, the sum of the partial charges in the aromatic system have to be below -0.2. Otherwise, the reaction will not go and the substitution will not happen. And finally, with all of these substituted aromatic compounds, we can use them as reactants in the alkylation reaction, where we will functionalize the amine nitrogen in the other ring of our scaffold. For this, we are using again the same reactor node with a third type of transformation with an amine alkylation reaction, and we will also use and we can also specify different reaction rules to have real and valid transformation that can also happen during a real chemical synthesis. And here you can see some of the final results, some of the final compounds that we can build this way and have in our virtual compound library. So this virtual compound library, depending on the building blocks and the reactants we are using, can be quite large. And even with medium-sized compounds, it's very important to do some property-based filtering on our virtual compounds, so that we will be able to select those molecules which have physicochemical properties that fall within the desirable property space. For example, in our case, we are going to find molecules that have an effect on a CNS-based receptor. So it's crucial that the molecules that we select can cross and penetrate the blood-brain barrier. And for this, we will have to check some of the key physicochemical properties of these molecules, of these virtual compounds of ours. And for this, we are going to use the CNS MPO score, which is a weighted scoring function that assesses 6 key physicochemical properties of the molecules. The CNS MPO score function was developed by Pfizer chemists who systematically analyzed the molecules which they were working in their CNS related projects. And finally, they found that those physicochemical properties that have the largest effect of the blood-brain barrier penetration ability of the molecules are the molecular weight, the log P, the log D, the polar surface area, the hydrogen bond donor atom count, and the strongest basic pKa value of the molecules. So in order to use the CNS MPO score for filtering of our virtual compounds, we are going to calculate these 6 parameters of our molecules. First, we are going to generate the major tautomeric form of the virtual compounds to be used for the upcoming calculations. And once we have calculated these properties for the molecules, we will transform them into score values or score contributions by using various scoring functions that you can see here. And as a result of this transformation, we will get the score contributions from each PhysChem property, and as a final step, we will add them together to have the CNS MPO score value of each of the molecules. And what's left after that is to use this CNS MPO score value in a simple raw filter node to narrow down the list of our virtual compounds to those molecules that have a high enough CNS MPO value that's above a certain selective threshold. So with all of this, we have now a virtual compound collection with good physicochemical property profiles, but now we will have to look for compounds that are, on the one hand, structurally similar enough to these best virtual molecules, but are also real or easily accessible analog molecules of these best virtual compounds. And for this, we are going to do a large-scale similarity search, where we will search for similar structural analogs of the virtual compounds in a subset of the NIME real database, which contains 170 million compounds. And for this, we are going to use the MedFast similarity search software, which performs an in-memory search and can be used to find structural analogs even in such large compound collections. The MedFast software is a server-based application, so in order to use it in a KNIME workflow, we will have to send web service and communicate with it via web service calls, which we can do with the REST web service nodes of KNIME. First, we will use a post request node, which will send the web service calls to MedFast to perform a similarity search in the NIME real database subset and find the 20 most similar analogs for each virtual compounds. And after that, we will have to do some generic data manipulation, for example, to extract these 20 most similar analogs from the JSON output of these web service goals. And we will also have to perform duplicate row filtering because the same NIME molecule may have been sent back more than one times. And after that, because because this first similarity search only returns the internal identifiers of the enamine analogs, we will have to transform and convert these internal identifiers into the SMICE representation of the molecules. We will take care of that by using this GET request node here. And after that, again, extracting the SMICE strings themselves from the JSON output of the GET request node, we will use the advanced mole converter to contain the SMICE representation of the analog molecules into the chemical structural representation of these enamine analog compounds. And as a result of this similarity search, we could find some unique compounds that are also real or easily synthesizable molecules. For example, with one of our virtual libraries, where we had originally 45,000 virtual compounds, we were able to find roughly 5,600 unique enamine-based molecules. And to have a more focused library of real accessible compounds, we can use again the same CNS MPO score-based filtering that we have used previously with the virtual compound library as well. And as a result of this filtering, we could remove those molecules which don't have suitable and don't have good enough physicochemical parameters. And with this, we are at the point where we have some feasible molecules, synthetically feasible molecules with good property profiles, but we can get further information to make the final selection, the final triaging easier, more informative. And for this, we are going to use some predictive model building and classification, activity-based classification of the remaining enamine compounds. So for this, we are going to use our imported input molecule set to build a binary classification model using the random forest algorithm. And with this build model, we are going to categorize the remaining enamine compounds as active or non-active molecules. So here you can see what's behind the predictive model building. After selecting a threshold, an activity threshold on the p-Campbell values of the imported input molecules, we will label them as active and non-active compounds. And then we are going to generate different chemical fingerprints for the input molecules. Finally, in the current workflow, we are going to use the ECFP fingerprints as descriptors during the model building. And after partitioning the input data set into a training and the test set, we will perform the model building with the random forest learner node. And then on the rest of the input data set, which we will use as a test set, we will use the random forest predictor node to predict the active or whether the molecules, the test molecules, fall in the active or in the non-active class. And finally, we can use the scorer node to see the overall accuracy of the build model, which is a bit above 83%. By this model is not a very high level or a very complex one, we can still use it to have an indication and an initial idea to see whether we can expect some molecules to be active, or we cannot expect them to show an activity on our receptor system. And once we have the built model, we will use it on the molecules that we have found in the enamine database and that we were able to keep after the CNS MPO score-based filtering. So we will predict them to be active or non-active ones, and we will also use a color manager to mark the different molecules, the active and non-active molecules in our output table. And now with this, we are ready to do the final compound selection and triaging. So for this, we can continue with using interactive visualization. For example, in this case, we will use a scatter plot view, an interactive scatter plot view, and some tile views to visualize chemical structures that are behind the points of the scatter plot. So we will plot each compound and their calculated, each real accessible enamine compound and their calculated CNS-MPO score, and we will color them by their predicted activity class, where the red ones are the ones predicted non-active and the green ones are the ones that were predicted as active. And then we can use the interactive selection with the scatter plot node to select the compounds that we want to take to the next round, to the synthesis round. And after that, what's left is some description and some background about the overlap analysis, where we want to check how large is the distance, the structural distance and dissimilarity between the virtual and the real space, virtual and the real chemical space. So for this, we are going to use a systematic structural similarity or structural dissimilarity calculation to see whether we got really far away from the space of the virtual molecules and the space of the input molecules, in order to make sure that with our enamine compounds we are really exploring a new part of the chemical space, and we'll be able finally to identify novel compounds in the enamine database. And to see the results of this overlap analysis, we are going to use again some interactive visualizations with building a view from a few histogram nodes, where we will display and plot the distribution of dissimilarities between the virtual molecules and their first, fifth, 10th, and 20th nearest neighbors, respectively. So these were the presentation and the description part of the webinar. And with this, I would like to switch to the KNIME Analytics platform. And then we can continue with the hands-on part. So here you can see the workflow in KNIME. And again, once you have opened the KNIR file in the KNIME Analytics platform and installed the Chemaxon nodes and the evaluation licenses, then please open the drug discovery workflow within the Chemaxon KNIME Spring Summit 2020 folder. And once you have it opened, I will hide these to have a bit more space. Once you have it opened, you will get this total view of the workflow. And now we can continue with trying and playing with the workflow, and where all of you can start running the nodes and see the results. So we will give you, let's say, 12 minutes, and we can continue at 15 minutes past 6 p.m. And during this time, we can also answer some of the questions that appeared in the Q&A box. Okay, so now I think it's time to continue and go through the workflow steps together. And with this, I hope I will be also able to answer some of the questions that you have raised. So Here in the description, and as you have seen, if you open the meta notes, there are also some a summary about what is happening in that meta node, in that step, what are the key points there. So first we will start with importing the input data set, and there was a question here about which or whether you should change which file to import here. So we have only provided one input data file for this first small importer node. This is called the CNS active compounds.sdf, and this will import for me these 3,200 compounds from enamine. These are the ones import the molecules from the Campbell database, CNS active molecules from the Campbell database with their Campbell IDs, molecular weight formula, and also the p-Campbell values, which we are going to use for building the classification model. So in every case, we start importing this data set. Of course, if you have another SD file with known active compounds or molecules for which you have biological data, please feel free to try out the workflow with that input file as well. And once you have it, and once we have finished the import, we can continue with the structure standardization. And while the process is going on, I will open this meta node and show you that here is where the standardization, structure standardization happens, followed by the calculations and smiles generation of the standardized chemical structures, so that at the end we will be able to use the smiles of the standardized molecules for duplicate filtering. And once it has finished the calculations, check the results. So compared to the original imported data set, we have only 3,251. So after the standardization, there were 6 duplicated structures in the data set, which was probably as a result, the result of the salt stripping or fragment removal. And now comes the chemical clustering and the scaffold selection. So again, let's start it, and after that we can see what's behind this meta node. When the library MCS is running, we have used and built in several structure and data manipulation steps here. So the actual cheminformatics happens only in the library MCS node. Everything else was needed to extract this final top level structure collection from the output data of the library MCS, because as you will see, the library MCS nodes gives the output the entire cluster hierarchy, the cluster tree, and to extract from it the top level MCS molecules, we needed to do some data manipulation. And after that, we also wanted to sort these top level cluster molecules based on their frequency. So how frequent, how many times they can be found among the input molecules. And besides this frequency-based sorting, we also wanted to select a scaffold which have a high enough average p-Campbell value. So we used these 2 parameters for sorting our data set. So let me show you first the output of the library MCS, where you can see the the cluster hierarchy. So each input molecules and every generated MCS-based cluster molecules can be found in the output of this data set. And from this, we extracted the top level ones and sorted them based on the frequency and the mean P-Campbell value. So finally, this was the top cluster that we found it, that we selected. It was found in more than 1,000 input molecules and had an average P-Campbell value of 7, which also above the mean value in this collection. So now comes the R group decomposition step, which can help us deciding which ligand positions on this selected scaffold we should functionalize, we should substitute. And if we look in the result table of the R group decomposition, then you can see that there are altogether 14 different points or atoms or positions on the selected scaffold, which could be substituted. But in majority of the cases, only hydrogen atoms were found in these positions in the input molecule collection. So finally, we selected these 3 or 2 chemically different sites. One of them was the piperazine nitrogen, and the other 2 was the 2 equivalent ortho aromatic carbon atoms. And we could also go a bit further and check what kind of functional groups were, what kind of unique different functional groups were found in these positions. For example, on the ortho aromatic carbons, you can find the unique substituents here. And the same can be done and checked. The same information can be seen for the piperazine amine nitrogen collection. So here you can find the different substitution groups, functional groups that can be found. This can give us an idea about what kind of functional groups, what kind of substituents have been tried in the past. And also we can take this analysis further and see which functional groups worked, which helped to optimize the structure of the scaffold, which didn't have that much. So it gives also us information about the structure activity relationship of these known CNS active compounds. And next comes the generation of the virtual compound library. First, the substitution of the scaffold aromatic ring, and then the alkylation of the amine nitrogen. So I will come back here and start the enumeration process. And then while it's running, we can take a look at how these virtual reaction steps look like. So for the nucleophilic aromatic substitution, we imported a set of building blocks which contain just a few reactants, just a few building blocks for us to be able to finish running the workflow. And then we used the reactor node where we have defined the virtual chemical transformation and the reaction rules. And then we started the transformation. So you can either import a reaction file containing this virtual transformation, or also you can draw it. or you can also add the specific reaction, and you can specify the reactivity, or in the case a selectivity rule, which checks the nucleophilicity value of the aromatic carbons. And you can also decide if you want to run a combinatorial reaction or just a sequential one. So if you want to, if you have if you have multiple compounds in your first and second reaction set, you can decide if you want to have a combinatorial set where each pair of reactants are reacted together, or you just want to go sequential. That order. And a similar process, very similar, identical process was used for the Friedel-Crafts alkylation reaction as well, to get the product compounds. And finally, these two collection of substituted aromatic compounds were concatenated and set to the alkylation reaction as starting materials. And for this alkylation reaction, we have to import a third building block collection, and this is where you can decide to go with this small building block collection and use the node as it is, or how it has been configured previously. Or if you have more time, or you want to try the workflow with a larger virtual compound collection, then you can also modify the file that's used here and use the reagent 3 large set as well to get these 45,000 virtual compounds instead of just a few that we are creating here. Because if we check the output of these 3 virtual reactions, then we will see that we have 280 virtual molecules instead of these 45,000. So now we can continue with the CNS-MPO score-based filtering. Where we first are calculating the 6 physical-chemical properties, and then we transform them into CNS-MPO score contributions using the different scoring functions, and then add them together to calculate the final score value for each virtual molecules, and then use a row filtering. So by definition, the maximum value of the MPO score is 6. Here we are using a threshold of 5. So any virtual compounds that have a value below that, we will survey and keep only the largest values, compounds with the largest values. And now comes the similarity search to find the analog compounds in the enamine database to set from the virtual chemical space to the real one. And by this, so here we had to perform several data manipulation and string manipulation steps. And here, of course, because we are using web service calls, this means that we need stable internet connection, which seems that I do not have at this moment. So in order to show you the entire workflow, I will probably switch to that version of the workflow that I have run previously and continue with that one. So we can go through the entire workflow. Yes, so this is the very same workflow that we have used so far, but most of the nodes have been executed previously. And here you can see the result of the enamine search and the upcoming duplicate filtering and the transformation of the internal enamine compound identifiers into a SMILES-based representation, SMILES-based structural representation. So we have this 113 unique enamine-based analog molecules, which we can send again to a CNS MPO score-based filtering, which uses the very same steps that we have used previously on the virtual compounds. And we will end up with 61 such molecules, the result of this property-based check and property-based filtering. And then comes the building and the usage of the classification model. So first we use the input data set to build the model. We use the histogram view to see the distribution of the p-Campbell value of the input molecules in order to select a threshold value to divide the input data set into active and non-active compounds. And we selected, for this threshold value, we selected the p-Campbell value of 7 to distinguish between active ones and non-active ones. And then we calculated and generated just a few chemical fingerprints, the chemical hash fingerprint and the ECFP fingerprints, and finally decided to use the ECFP. As I mentioned, this model isn't a high-level one or complex one at all, and we didn't find or didn't try any other descriptors or descriptor sets for this. We just wanted to demonstrate how such a model building and prediction step can be used as part of this drug discovery workflow. So we partitioned the input data set, used the random scorer, and then the random forest learner, and then the random forest predictor node. And then with the scorer node, we could check the accuracy value, which is again close to 83%. And then we also used the build model on the input data on our enamine-based molecules. And if I go back to the main view, to the main workflow view, and we check the final result of this activity class prediction, then you can see the predicted class, the active or non-active class of the 61 remaining enamine compounds, and also the confidence of the prediction that was calculated for them. You can see a few active compounds and the red ones, which were predicted as non-actives. And then we used and built a component view, a component node for the interactive visualization and the visualization-based selection, where we use the scatter plot node and the tile view to display the structures, to display selected structures. So if we open this interactive view, then we will be able to do this final compound triaging and selection with it. And so here we have the compounds, their calculated CNS MPO values, and the red dots are for non-actives, the green ones are for the actives, and the tile views will show us those chemical structures which we select in this interactive view. So first, to make this selection, I will switch off the non-active ones, because I'm only interested in the actively predicted ones, the green dots, and then I will select. So in this set, we found 5 active compounds. So we can decide to keep only these three, but which has an MPO score above 5.5. And once I have active selection, the tile view will show me the chemical structures behind these 3 points. And we can also use this node in a way to store the selected state of the compounds. So if I choose here the close and apply, then the output of the component node will store for me the selected or the non-selected state of the compounds as true or false values, so that in the next step I can use a row filter node to keep only those where the selected state is true. So if I execute it, I will have 3 molecules which have high enough CNS MPO value and which are predicted active and which come from the enamine wheel database, which means that they are also synthetically feasible molecules. So these 3 are probably worth to be sent in the next step to organic chemists who can synthesize them for us for the next round of tests. And to do that, we can finish workflow with exporting the 3 molecules with the mole exporter node into an SD file. And we have the final result. And what's left here is just the overlap analysis, where we are doing this comparison, structural similarity-based comparison of the enumerated virtual compound space and the enamine and the real chemical space of the enamine analog molecules. And as a result of this loop, we can calculate or generate a table where for each virtual molecule that you can see here, we calculate the dissimilarity of their first, fifth, 10th, and 20th nearest neighbors, nearest neighbor analog compounds. And if we use again a component view in which we have built in 4 histograms, then we can check how these dissimilarity distributions look like. So we can see, as we are considering nearest neighbors that are less and less similar to the original virtual compounds, we can follow with these histograms how we are getting larger and larger dissimilarity values. Okay, we have only a few dozens of compounds here, so it's not a large collection. If you try the other building block file and generate the large virtual library, then you will see a much better results here. But it can be found here as well that only with the comparing the virtual molecules and their first nearest neighbors, so their most similar analog from the enamine database, most of the dissimilarity values are above 40%. So even with this first step away from the virtual space, we are taking a larger distance or a larger steps from the original space. So at the end, we have a good chance that we will find really new novel compounds which have not been tested. And this was it basically, what we wanted to share. And I hope you found it useful. So if you have any questions now or later on, then please feel free to contact us. We are going to share with you the slides and also the recording of the presentations. And thank you very much again for being here and for participating in the workshop.
And let me add to actually one thing to this is that several of you are experiencing request timeout and timeouts when you're searching for the enamine real database. it is because the server got overloaded a little bit. So we are working to bring it back to speed. We are sorry for that. It's cool because actually we tried it on so many people actually how that works. So we already executed a load test on that. Sorry for that, guys. And if you come back later to that, I'm sure it will work.